This lesson is going to focus on Chapter 1.3, which is exploring properties of parent functions. In mathematics, every function can be classified as a member of a family, and each member of a family of functions is related to the simplest or most basic function sharing the same characteristics. And we call that function the parent function. We're going to talk in this lesson about four parent functions: the square root function y equals root x, the reciprocal function y equals 1 over x, the absolute value function y equals absolute value of x, and the cubic function y equals x cubed. Starting with the function y equals root x. Well, we can see that given this rule, we could make a table of values, and we could let x have the values 0, 1, 4, and 9. And if we do that, then y would have the corresponding values of 0, 1, 2, and 3. Because if x is 0, y would be the square root of 0, which is 0. If x is 1, y would be the square root of 1, which is 1. If x is 4, y would be the square root of 4, which is 2. And if x was 9, y would be the square root of 9, which is 3. Now, if we were to then graph those points, they might not show up too well, but here they are I'll color them in blue. And if we were to graph those points, they would look like this. But of course, we know that the function would go on, continue to go on towards the right, because any positive number can be used for x in this equation. So our domain would be x greater than or equal to 0, since any positive number can go in, or 0. And so our function would look like this with an arrow pointing to the right. Now, to explain that a little bit further, why that's what our domain is and why we chose the points we chose on our table of values, we know that the square root of -1 doesn't exist. And similarly, the square root of any other negative number doesn't exist. That's why we started our table of values with an x value of 0. And we see that the square root of 2 is approximately 1.4, which is difficult to graph, and the square root of 3 is approximately 1.7, which is difficult to graph. The square root of 4 is 2, but then the square root of 5 is approximately 2.2, which is difficult to graph. And so we can see that while we can approximate the value of the square root of positive numbers, it's likely best for graphing purposes to focus on taking the square root of perfect squares. So for that reason, we only use perfect squares in our x values column of our table of values. So hence, this is why we use the values of 0, 1, 4, and 9 for x, and why we have the corresponding values for y. And that when we plot them, we get these points here. And then we realize the smallest value x can be is 0, but then we can go on forever in the right direction and continue the behavior of the function. Now, the next one we're going to look at is y equals 1 over x. This is called the reciprocal function. And we see that x cannot equal 0 in this case. You cannot divide by 0. We can't have 1 divided by 0. So we see right away, when we do make our table of values, we cannot have an x value of 0 in that. And we also see, because since y equals 1 over x implies y equals 1, which implies x equals 1 over y, we see that y can't equal 0. And as we'll see when we graph it, this means that we're going to end up having an asymptote at x equals 0 and an asymptote at y equals 0. So using our table of values, we'll put in some points that we think would be good to use. We'll try an x value of -5, which would lead to a y value of 1 over -5, or -1/5. We have an x value of -2, which leads to a y value of 1 over -2, or -1/2. An x value of -1 leads to a y value of -1. An x value of -1/2 leads to a y value of 1 over negative a half, which is negative 2. And an x value of negative a fifth leads to a y value of 1 over negative a fifth, which is negative 5. Now, like we said, when we have an x value of 0, our y would be undefined. But then we would have, we would continue the pattern established with the negatives when we say that if x is a fifth, y would be 5. If x is a half, 1 over a half, y would be 2. If x is 1, y would be 1. If x is 2, y would be 1 over 2, which is a half. And if x is 5, y would be 1 over 5. And we plot those points like this. We see the points in red, and I'll just show them off a little bit more clearly. That's the point 1/5, comma 5. That's the point 1/2, comma 2, 1, 1, 2, comma 1/2, and 5, comma 1/5. Over on the left-hand side, we've got -1, -1, as well as -2, negative a half, -5, negative a fifth, negative a half, -2, and negative a fifth, -5. And we can then join them with a curve. Now, this curve is in two parts, and we see that the y-axis acts as an asymptote. It looks here, because I'm using thick magic marker, that the curve touches the axis, but it actually doesn't. This curve will get infinitely close to the y-axis, but will never touch it. And similarly, on the right-hand side, the curve will get infinitely close to the x-axis, but it'll never touch it. Down here, the same thing. The curve gets infinitely close to the y-axis, and over here the curve gets infinitely close to the x-axis, but never touches it. Now, since it's difficult to graph fractions, we usually just use the following points for our table of values. We use the point -1, -1, and the point 1, 1. And then we make sure that we remember that we have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And when we then come to graph more complicated versions of these functions after they undergo transformations, we'll see that this is enough to get us through. Okay, the next one we're going to talk about is y equals the absolute value of x. Now, the absolute value is defined as the distance a number is from 0. So if we were to try to consider the absolute value of -3, we might draw the number line like this, put a 0 here, -1, -2, and -3, and then we would try to establish the absolute value of -3. In order to do that, we would calculate its distance from 0, and distance has to be non-negative. So the distance of -3 from 0 is 1, 2, 3 units. So the absolute value of -3 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. It's 0 units away from 0. The absolute value of 1 is 1, because it's 1 unit away from 0. The absolute value of 2 is 2, and the absolute value of 3 is 3. Okay, so just to repeat what we said, the absolute value of a number is the distance of that number from 0. And since distances are always non-negative, the absolute value of a number is always non-negative. The absolute value of 3 is 3. The absolute value of 0 is 0. The absolute value of -2 is 2. Graphing the points that we had on the table of values we just created, we would have 0, 0, 1, 1, 2, 2, and 3, 3, as well as -1, 1, -2, 2, -3, 3. Our points would continue on to the right in the same manner forever, and our points would continue on towards the left in the same manner forever. And this is what our graph would look like. And finally, we talk about the cubic function, y equals x cubed. Well, we can let x have various values, -2, -1, 0, 1, and 2. If we cube -2, in other words, -2 times -2 times -2, we get -8. There's a mistake there. If we cube -1, in other words, -1 times -1 times -1, we get -1. If we cube 0, 0 times 0 times 0 is 0. If we cube 1, 1 times 1 times 1 is 1. And finally, if we cube 2, 2 times 2 times 2 is 8. And so what we're going to do now is graph these 5 points. In doing that, we have -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. And now we can draw a continuous curve through in both directions, and we have an idea of the graph of the curve y equals x cubed.